Before we begin, we'd like to thank the National Science Foundation Office of Polar Programs for their financial support to ARCIS and this seminar series. Now I'd like to welcome today's presenter. Dr. Thomson studied applied ocean physics and engineering at MIT's joint program with Woods Hole Oceanographic Institution, receiving a PhD in 2006. Dr. Thomson studies waves and turbulence at the surface of the ocean, including interactions with sea ice. His work emphasizes field measurements and physical processes and includes the development of instrumentation and autonomous platforms. Dr. Thomson will also participate in the NSF-funded Polar Trek program later this year, hosting educator John Pozzol during the Coastal Ocean Dynamics in the Arctic expedition aboard the RV Sikuliak. Now, today, Dr. Thomson will be discussing ocean waves in the new Arctic. Please help me in joining Dr. Thomson. Thank you. And we'll turn the video over to you.
Okay, is everyone seeing the first slide with a pancake ice on it and hearing me well?
Yes.
Okay, great. Well, I would like to explain this picture to you over the next 45 minutes or so, and some of the things we've seen in the last maybe 5 or 10 years of research that are related to this picture. And this is a picture of pancake ice collected in the Western Arctic in the Beaufort Sea. And there's a buoy in the center of the picture. That's one of the swift buoys that we built here in my lab that we use to measure the waves and the other processes happening near the ocean surface while this is happening. But first, I'll give you a quick backdrop. Most of it's probably familiar to those of you who work in the Arctic, especially the Western Arctic. And the first part of it is just that there's less ice. And so we know that at the seasonal ice minimum in the summer, late summer of 1980, there was a small stretch of open water between the north slope of Alaska and the main ice pack. And then in 2012, that was enormous. It was something that had grown by a factor of maybe 5 or more. And that it varies year to year, but the general story is the same. At the seasonal ice minimum around the end of September, there's a lot more open water than there used to be. There are all sorts of big implications for that. People talking about northern sea routes and things like these red lines that I've drawn here. There are also a lot of implications for the physical system and the natural system. Not only is there less area coverage, but there's also a real change in the ice type. And so this is a progression through the last few decades of how much ice is multi-year ice, and those would be the red colors in this series of maps, and what is first-year ice, and that's in the blue colors. And basically, there's just a lot less multi-year ice. And so the ice that remains season to season, interannually, is much thinner and is much weaker and is not the thick multi-year ice that used to populate a lot of the Arctic. So not only is there less area, but there's less volume and less quality, basically. And so this is something that many have been trying to forecast and understand. And on the panel on the right here is different projections of what the aerial ice extent should be in plan form area. And there's all these different models, and they all have different flavors and things, but they're nominally showing this trend and then a wide standard deviation around the trend. And that's the blue and the yellow lines, the gray is the variations. And they're not keeping up with the observations. The observations have been showing a steeper decline in the total pan-Arctic ice extent. And so that means the models are missing something. And there are a lot of different things that, a lot of two-way coupling that's not yet in the bigger models. And there are a lot of things to consider. One of them that we've been focused on is the interaction with ocean surface waves. And so that's what I'll spend the rest of the day talking about, is what we've been learning in that regard and where we see coupled modeling going in the future. So I think I'll skip these and move right on just to this schematic. The schematic was developed by Mark Harris, who came into the field with us in the summer of 2014 as an embedded journalist and was a participant in all of our field work. And then he wrote a piece in Scientific American. And so if anyone is looking for a sort of a not very technical but still accurate review of some of these processes, or wants to share this with a larger audience, family and friends, I think this piece in Scientific American was very nicely done and included this nice graphic, which shows you some of the feedbacks and different mechanisms we've been looking at. So in the very back part of the graphic, there is just a wind blowing over an ice sheet, a contiguous ice sheet, and that would move that ice sheet around and cause some stresses and lots of, a whole flow size distribution. And there's some open water, and that open water is where waves can be generated. Eventually the waves propagate into the ice, and two things happen. One, the waves are attenuated by the ice, so the ice affects the waves, but the waves might also fracture the ice and break up the ice or change ice formation processes. And either way, it's a two-way process, right? The ice affects the waves and the waves affect the ice. So that's, as a larger theme, that's what we're interested in, is those processes going both directions. The schematic also includes a lot of things about how we were making these measurements in 2014, a real variety of autonomous platforms and moored platforms and shipboard measurements, and a full suite of instrumentation to try to do this over wide domains. And that's another topic and another theme that I think is important here, is to all the work that we've been doing and other colleagues here at APL and across the community on trying to really push the level of autonomy in doing this as distributed sensing networks, instead of the traditional approach of let's just take an icebreaker out, park the icebreaker next to one ice floe and make one measurement. We're trying to really cover the spatial temporal signals a bit more completely in our modern sampling. Okay, so let's cover some basics in the next few slides. First, here's how we understand ocean wave dynamics. At the fundamental level, all the waves come from the wind. The wind acts over some distance, and we call that distance the fetch, and it acts for some period of time. And so with more time and more distance, you can accumulate more energy in the wave field, and the wave field can mature. Our approach to that in a numerical sense is this wave action balance. This is the equation I've written here, and I promise these are the only few equations I'm going to have in the whole talk, but it just sets a few things up. So on the left-hand side is the total change in the wave action, that's symbol N. And on the right-hand side are the sources and sinks, the things that make that increase or decrease. And so our typical approach is this next equation, which those sources and sinks, they have input from the wind. They have nonlinear transfers, which move energy around between different frequencies in a spectrum of waves, but they don't actually change the net amount of energy. They don't increase or decrease energy. They just move it around in a spectrum. And then there's a dissipation term, and that's usually due to white capping and due to breaking, and that's where energy is lost from the wave field. And so these things all balance out to tell us how the waves evolve. In ice, our approach is to add another term, that's this S ice term. So that's a source, or really a sink term in the ice, where energy is lost to the ice. And so this is an overall modeling framework. A lot of people have contributed to this. One of the bigger contributors has been Eric Rogers at the Naval Research Lab, and so I'm referencing his work here. And one thing that's key about this is all done spectrally, by which I mean this is done at every frequency of the wave field. And so just a short cartoon on that, that's because waves in the ocean are a random stochastic process, and they're very broad band. They have a lot of different frequencies. So I just mean to be clear about the distinction between the upper panel, which is a single sinusoidal monochromatic wave at one frequency, and that is not what we have in the ocean. What we have in the ocean looks like this second signal, where all the waves are a little different, not only in amplitude, but also in their frequency, how closely packed or spaced they are. So we want to describe the whole spectrum of waves at every frequency. And so that equation I was just going through is done per frequency. And then we put it all back together to figure out what actually happens, in the time domain, how you experience waves. So I'll circle back to that in a minute. I just wanted to make that part clear. So a little more on the basics, which would be a history lesson. For the landing at Normandy on D-Day, there were wave forecasts made. And those wave forecasts were done by Sverdrup and Monk, two very famous oceanographers, and they had an analysis, a pretty simple analysis that they made to try to understand how big the waves would be that day. And they did this scaling according to how much fetch was available for the waves to build. They used a non-dimensional scaling, and what they did is they normalized everything they were working with by the wind speed. So they said, given a wind speed and a fetch, what is the wave energy, or the wave height squared, but what is the wave energy that we should expect to observe? And so they ended up with a non-dimensional fetch scaled by the wind speed, and they said, okay, given that fetch, what energy should result? And it was quite successful. Obviously, D-Day was successful, and this is an approach that has persisted for a long time, and with some refinements, but it's been remarkably robust. And so we have been applying this in the Arctic with similarly successful results. So let me walk you through some of the first steps of that and some of the nuances of that. First, we started with observations. There have been a set of moorings in the Western Arctic run by the Woods Hole Oceanographic Institute as part of the Beaufort Gyre Observing Program. That's an NSF program that's been running as a long-term observational effort for well over 10 years. It's getting close to 20 years, I think. And they have these moorings in the Arctic where they invited us to add instrumentation. And so in 2012, we began adding these up-looking sonars that are specific to wave measurements. They also do ice draft, which is a more traditional use of up-looking sonars, but this new instrument was in particular for wave measurements. And so in a collaboration with them, we added our instruments to their moorings, and this has been ongoing since then, and the data record continues today, and we're hoping to get the next round of data back this coming open water season. And so 2012 was the first data set, and we saw that early in the season, we had small waves. And so here's a time series of the full record from August until November. That was the open water season over this mooring site. And early on, the waves were on the smaller side. And then later in the season, we had this dramatic event where the waves were 5 meters. That is remarkable in the Western Arctic in general. Those are just enormous waves compared to what's conventionally been reported by traditional knowledge and what's been seen by previous efforts there. 5-meter waves, that's a big event. Those are really energetic waves. And so we have spent some time trying to understand that particular event and what happened there. And many of you might remember the Great Arctic Cyclone of 2012. This was not that event. That event happened earlier. That happened in August. But that event was part of this story. That event opened up a tremendous amount of open water. It really, really knocked back the ice pack. And so now there was a lot of open water or a lot of fetch. And when this second event came in September, then all that fetch was available to build big waves. So we've done some modeling. Eric Rogers has run this model that's playing in a loop now, where the color scales the wave height, again, going up to 5 meters. You can see on the left-hand side, there's Alaska, and in the Beaufort Sea north of Alaska, this becomes an enormous wave event, and it's really because there's so much space available. There's so much open water available for the waves to form. You can see there's a little diamond, a little symbol where the mooring is located, and again, that record continues today. And so that's what happened in this event. We analyzed that event and analyzed the entire data set in terms of the open water fetch available and came up with this result, which really collapses a lot of the data. There's several orders of magnitude of wave energy observed, and it's well correlated with the available fetch. And that available fetch is predominantly set by how much, or where the ice edge is, basically. So we're really just tracing back along the wind direction until we hit land or until we hit ice. And that turns out to be a simple way to understand how big the waves are at any given time. There's some other interesting things in this. There's definitely some scatter. The grayish points that are the most scattered off of the correlation line, those are when there's ice present, and then we expect different things to be happening. There are also some symbols that have an open symbol here, and those are waves that are particularly mature, by which I mean we use a metric called the wave age, which is the ratio of the wind speed to the wave speed. And those waves aren't really being directly forced by the wind anymore. So the fetch analysis is a little bit not exactly as designed in that case, but I think it's showing us that these most energetic cases, they are becoming a mature sea, which is what we call swell. And swell, of course, the rest of the world's oceans have swell. The Western Arctic has not really had swell before because there hasn't been enough space available for the wave field to mature that much. So not only are we seeing this dependence on the fetch, we're also seeing an emergence of a different wave type in the region. But first about that ice part. So this gray line, the gray symbols there, they are when there's ice and they scatter off that line. They're doing something different. And so PhD Maddie Smith, she's a PhD student, recently finished. One of her chapters of her thesis was a paper looking at this and trying to understand when there is partial ice cover, can we still apply a similar analysis? And it turns out to work pretty well. She came up with a concept for an effective fetch, which is basically a discounted fetch. When you're in partial ice cover, then let's say you have 10 kilometers of a marginal ice zone and it's 50% ice cover. Then maybe you shouldn't count that as 10 kilometers of fetch in the traditional sense. Maybe it's effectively 5 kilometers of fetch, say. And so here is an empirical result that she came up with using some of our field data that shows how the effective fetch is decreased by ice fraction. And indeed, more ice fraction, less effective fetch. So this this explained our observations pretty well and was able to carry that fetch analysis forward a little bit and be able to use it in a marginal ice zone where there's partial ice cover. Continuing, we've been trying to look at some of the larger scale trends that that are really the manifestation of these fetch dependencies. And so in a paper a few years ago in ocean modeling, we looked at the trends in the ice, and that's what this map is here. This is the basically the extension of the open water season, or really the days per year that the freeze up is becoming later and later and later. And so in the Beaufort and Chukchi Seas, which are just north of Alaska there, these red colors show a trend that the open water season is lasting about 1 day longer each year. This analysis is done over 30 years, so that means that in these regions where the red colors are, the open water season lasts almost a full month later in the year than it used to. And that is certainly anecdotally confirmed by spending time up there and also talking to people in the villages that it's open water along that part of the coast, often into November now, where it used to be freezing up in October. And so, coupling that extra amount of time with the fetch scaling that I've already shown, we can then look at, well, now that there's not only more space, but more time available for waves, is the background sea state increasing? And so that's what we did in the second half of this paper. And indeed, here are the trend lines. The background sea state is dramatically increasing. The upper panel are the average wave heights throughout the domain. The middle panel are the wave periods, and the lower panel are the wind speeds over this. Now it's a 20-year record. This is not a data record, but it's a hindcast with a wave model run over that whole domain for this period. And so the trend in wave height is pretty clear. The waves are definitely getting bigger. Every different storm is different, but in general, at any given location, there will be larger waves, more wave energy. The wave period's also increasing, and that's related to what I was saying earlier about the waves becoming more of a swell-like wave. That longer period is more like swell. And those longer period waves, they actually carry more energy because they travel faster. Their energy flux is increased. So really, to have an estimate of the total amount of energy moving through the system and arriving at the ice edge or arriving at the coast, you really need both of these trends, because that calculation of the energy flux includes both the wave heights and the wave period. So the fact that both are increasing is important. The wind speeds seem pretty stable. There's been a lot of other work trying to understand what the weather patterns are doing in this region, and some do show significant trends. So, for the purpose of running this model and these results, there need not be any increase in the winds to get this increase in the waves. All we need is less ice. We just need more fetch for longer periods of time, and you will build bigger waves. The winds, at least in our analysis, aren't changing, although I realize some other literature shows that it probably is. So now that we have all this, we can ask what's happening not only in the fall, but throughout the whole annual cycle. And so, of course, the annual ice cycle is very dramatic in this region. Here's one example of that, one plot of that, where the ice decreases throughout the summer season and then rebounds and reforms. And so I'll just highlight for a moment some new work that's ongoing, trying to understand the whole seasonal ice cycle, whole annual cycle. And that's part of a program called CODA, the Stratified Ocean Dynamics in the Arctic program. This is an Office of Naval Research project, which included a lot of autonomous assets and a few different field efforts. But what I'll highlight here are 3 moorings that were put out, that were out for a whole annual cycle and were just recovered this past fall 2019. So they were out from September 2018 to October 2019. And the line of moorings basically traces right between the array of the Beaufort Gyre moorings that I was talking about earlier, that are an NSF-funded effort. And so we were trying to complement that effort and get a higher resolution data set of a whole annual cycle. PhD student Sam Brenner is working on this data set, and here's some of his results, looking at the waves throughout the open water season and the wave periods, and showing that these agree with the models pretty well, and showing that that the season we had was a pretty active season. He also has a record that goes through the winter of the ice thickness and the water column velocities and the temperatures and salinities. So he will have a poster at the upcoming Ocean Sciences meeting, and look forward to his work in the coming years on trying to put together the whole annual cycle and seeing how the waves are related to that. Now, I want to step back to just what the waves are doing in this picture, and particularly what the waves are doing in the fall. And we've spent a lot of time in the field in the fall the last 5 years or so, and we've routinely seen things like this. This is a movie of Pancake Ice. This was recorded from Sikuliak, which is the Arctic research vessel run by the University of Alaska Fairbanks. This particular video was in 2015. The waves are about 3 or 4 meters in this video, and you can see them roll through, and you can see the Pancake Ice is moving with the waves. And this is a movie that would be very common to see in the Antarctic, because the Southern Ocean always has big waves, and there's always a lot of wave action. It had, traditionally, I would say this is a rare thing to see in the Arctic, that the wave climate has increased dramatically, that this is a much more common thing to see. So if you're not familiar with Pancake Ice, this ice formation really only occurs when there are waves. As the frazzle ice forms and floats to the surface, it will basically flocculate and make these smaller collections of ice. And then with wave motion, those collections will start to bump into each other, and they will start to form these pancakes with these upturned edges. And there is a strong relationship to the wavelength of the waves. There's been some nice work by Maddie Smith and Letty Roach in understanding those dynamics. It's building on the work of Haley Shen from earlier analytic and lab measurements, and now we're seeing in the field. And so this is an ice formation type that's quite prevalent now in the fall Arctic, I think. And so this is a great example of the waves affecting the ice formation, and also the ice affecting the waves. So I'll spend a little more time looking at the details here. And here's, again, work by Maddie Smith and her recent PhD dissertation showing exactly how the pancakes move as the waves roll through. So here's a schematic here showing the wave orbital motion. So in open water, that's the top panel, as a wave moves through from left to right, then the particles at the surface are tracing out these orbits in deep water. And when there's ice on the surface, the ice is mostly tracing out those orbits also. But in a model developed by Haley Shen several years ago, the ice is basically sliding down the front face of the waves, and so may have some small relative velocity to the water that it's in. So that would be a delta V. And then it's sort of accelerating down the face of the wave, almost surfing the face of the wave. And then on the backside of the wave, it also has relative velocity. It's not quite keeping up with the wave. And so it would have a little bit of relative motion. And that relative motion is probably related to the overall kinematics, or it is the overall kinematics, and it's related to the overall dynamics also of how the ice is forming, and also how wave energy may be being lost from the wave field. And it's lost to trying to force this ice to move, trying to move this ice around. So here's an example of Maddie's results where she's using stereo cameras to map the ice motion as the waves come through. She's doing it in a phase resolved sense. And what I mean by that is we are tracking individual waves as they come through. The upper panel are the wave elevations. Those are the symbols eta. So this is the actual displacement of a wave as a wave comes through. The next panel are the velocities of the wave itself, of the surface. And then these are the average diameters, distances of the pancakes. And then the bottom panel are the delta V's, the relative motions of the pancakes to the water. And they turn out to be very small. So the takeaway from this is that the pancakes, they mostly move with the wave orbital motion. They're mostly doing what the water's doing. And that makes sense. They agree with this slope sliding model from Haley Shen, and an updated model from Herman 2018 that includes some more details to an added mass to the ice as an object. But the point is that those relative velocities are small, and yet there's still enough to generate turbulence in the water column, which may be associated with the dissipation of wave energy. So let's look next at that. What's happening to the waves in this environment? Well, the wave spectrum is becoming attenuated. And so this plot shows the wave energy as a function of frequency. And this is how we typically look at wave data. We look at a collection of waves over the course of an hour, 30 minutes or something. And we use the Fourier transform to make a spectrum and look at where the energy is located. And so in that event, in open water, a red line was a swift buoy in open water. There is a peak in the wave energy, and then there's this high frequency tail that extends like this. And that goes as frequency to the -4th power, and we have a lot of good dynamic understanding why that is. That's in open water, though. And as soon as you are into any of this pancake ice, that high frequency tail is reduced, it is attenuated. And so the full story here is that the pancakes they're basically scrubbing on the water surface because they have that delta V. They're not quite keeping up with the water. And that is extracting some energy from the wave field and turning it into turbulence. And the amount that's extracted is the difference between the red spectrum and the blue spectrum. And it's preferentially occurring at the highest frequencies. If you look at the lower frequencies, if you look at the peak in the waves, there's almost no attenuation whatsoever. And I think you see that when you watch the video, right? You see this clean swell rolling through the video and a very smooth surface. It's smooth because the high frequency waves are gone. It would have been rough if you were out in open water looking at the red line, but inside the ice cover, the blue spectrum doesn't have any high frequency components, so it's very smooth, and you just see this pure signal of the dominant waves. And so a lot of our work has been to tune and calibrate models that can reproduce this, knowing the ice type or having the ice type as an input from some of the other models, like SICE, like a community ice model, for example. And this is work reported in a paper by Eric Rogers in 2016. And it uses that same spectral balance. So this is being solved at every frequency. So that's how we're doing that. We've seen some more evidence of this during the recent CODA project, and I won't spend a lot of time on this, but I'll just show you another example of working at an ice edge and having some buoys outside in open water and some buoys in the ice. And here in the upper panel, looking how the wave heights change. The yellow or gold colors are the offshore buoy. Their wave heights are constant out in open water the whole time. And then the other buoys, these blue and red symbols and the purple symbols, they're buoys that are released in the marginal ice zone. And over the course of a few hours, they are absorbed into the marginal ice zone and they get into regions that are very, very small waves. So they lose almost all of their energy. We see those changes in the spectrum. And then as a further part of this story about the turbulence, what's happening with the turbulence, we see changes in the profiles from the surface to a few meters below the surface of the turbulent dissipation rate. And that's this bottom right panel here. And this is a unique measurement that we make with the Swift buoys that allows us to see how much energy is being lost in the upper few meters of the surface. And so I think in these events, in these storm systems, and when the waves are propagating the ice, a lot of what's happening is really happening very close to the surface, in the upper few meters of the surface. And that's, again, where this theme of autonomy comes in, because that's a very difficult region to sample with a ship, right? The ship has propeller wash and has a wake and has all of these effects that really contaminate the data in those first few meters of the ocean. So that's where we use these autonomous buoys to collect that kind of data and really have a clean picture of what's happening there. And so we see a lot of the energy that's lost by the wave field being lost in that upper few meters of the water column. Some of the other effects we were looking at in that same data set are how the waves can affect the ice edge and move the ice edge. And so here's some work that's very much ongoing and is not at all complete, but I'm hoping to present some of it at Ocean Sciences. So I have 10 days to pull it together. There are radar measurements of ice drift velocities. These are by Bjorn Lund and the group at the University of Miami. And so the little vectors here on this radar overlay where there's open water out here and a marginal ice zone here. And we're trying to understand how the waves may, through their momentum, may be pushing this ice around. And so the waves in this case are coming in this polar plot. They're coming from the east, going towards the west. So they're pushing this ice towards the west, and that's indeed what the vectors show. And we're looking at an analogy with the type of alongshore flows that happen at a coastline, that happen in a surf zone, where the waves carry momentum, and then when they get into the surf zone, they lose their momentum, they release their momentum, and they drive a current. We think something similar happens to the edge of the ice, where the waves, as part of their process of losing their energy, they also lose their momentum, and they move the ice around. And so you might say, well, we also know that the wind moves ice around, right? And that's been the canonical model for decades of understanding ice drift is that the wind's pushing it around. The difference here is we're looking at something highly localized. And so sure, the wind moves around the large scale ice motions, absolutely. But again, remember that the waves integrate the wind over a fetch distance. So the waves become this very concentrated way to transport the energy momentum that was in the wind field. And then if they release that all at once in a marginal ice zone that's only a few hundred meters wide, there's really a tremendous amount of energy and momentum that can be released or dumped into the ice field. So we're looking at something that's much smaller scale and really trying to understand the ice edge relative to the overall wind drift kind of patterns. Okay, I want to now come to sort of the final section of the seminar and talk about what's happening at the coast, because that's the project that we're doing right now, and that is, I think, some of the more immediate things to to people who live there. So this project is called CODA. You note the analogy with soda, right? We're very creative with our project names. So this is the Coastal Ocean Dynamics in the Arctic project. There are a bunch of collaborators involved. So there's Nirni Kumar, also here at the University of Washington. Lucia Haskova is sitting to my left here and is a big part of this work. And then Eric Rogers at Naval Research Lab is also involved. And we really were motivated by this picture, which was taken in Utjarvik, formerly Barrow, that was taken 2 years ago in the fall, when there was a big wave event that impacted the coast, and large portions of the village flooded. A large part of Stevenson Road that goes out towards the Gnarl, that was flooded, and some of these freshwater areas back here were inundated with salt water, so there was a water source concern. Boat ramp was destroyed. There was really a lot of infrastructure damage. A lot of things happened. This was a big event for the community. And so, clearly there's the wave forcing is sort of fundamental to an event like this. And so we're trying to understand, how often is this going to happen in the future? Can we forecast these events? Can we have a better set of expectations for what's happening? And do we understand what's happening, at least in the natural environment, but for an event like this? And then hopefully future projects understand what's happening in the built environment for these projects. So that's the background for that project. Here is some more background. This is work by others. This is from a publication by Gibbs, looking at what the rates of erosion are along the coast. And this is along the North Slope. So the Brooks Range would be down here, and this is all on North Slope. There's Point Barrow, Prudhoe Bay is over here. And the color scales are the rates of erosion and as a shoreline retreat metric. So how many meters per year is the shoreline going backwards? And it's typically a few meters per year at many sites. That's the yellow colors. The red colors are more extreme. Drew Point has been a real focal point for people looking at permafrost bluff collapse. There's been a lot of nice time-lapse video of that you can find online, work by Jones and others, some nice publications on that. And those are the regions that are 10 meters per year that are really extreme shoreline loss. But across the whole region, maybe 1 or 2 meters is more of a typical number. And so we're trying to understand how much of the waves forcing that. And there's really a couple different ways to look at it. Part of what's happening along this coast is really that the permafrost is melting. And that's mostly a thermodynamic story, right? That's really about water temperatures. It's not so much about the mechanical act of erosion by waves, although you do have to have the waves bring the water up to the bluffs and to the permafrost for the warmer temperatures to melt the permafrost. So that's a coupled story. But there are a lot of other sections along the coast that are not permafrost bluffs, like the Drew Point case. There are more of a barrier island system. There are gravel beaches and sandy beaches, systems like that. And those really are most vulnerable to mechanical reworking, the kind of wave processes that are more purely mechanical. So one question we've been asking is if we can relate these overall trends to the trends in the wave climate. So I showed you about 10 slides ago that the wave climate is increasing something, like tens of centimeters per year in terms of the average wave height of the whole domain. And so we are asking if that equilibrium wave condition is changing, would the equilibrium coastline change? So this is a concept that's been applied at some mid-latitude coastlines, most notably along the California coastline, where people have looked at how the coastline adjusts from its equilibrium state. So the idea here is that the equilibrium state for the North Slope of Alaska is a state in which the waves are very small and are infrequent because there has not been much fetch and the ice is, there's shore-fast ice a lot of the year. And so that coastline was in a historic equilibrium that had very small waves. As the wave climate increases, the equilibrium shoreline will have to retreat to adjust for that and develop a new shape and develop a new position. And so we've only just started on that, but I'll show you a preliminary result. It's not something ready for publication yet, but it's fun to show. And in this result, the bottom panel is the change in the wave energy from that wave hindcast. And so the waves are increasing from the 90s until present day. And then the top panel is the shoreline retreat rate in meters per year. And we find that in this model, it was a very simple model, but it would have an average of something like 1 to 2 meters per year of a shoreline retreat, which is indeed what is in this Gibbs publication. These yellow colors are about 1 to 2 meters. So that at least at first order, that scales well and holds together. So that's one of the large scale picture questions we're asking as we go forward in this project. Of course, we're also doing some more detailed work. We're working at 3 field sites. So here are the 3 field sites. They are at Icy Cape off over here between Wainwright and Point Ley. And then they are the Jones Islands, which are to the west of Prudhoe Bay. And so Nuiqsut's over here, Harrison Bay is over here. And then the Flaxman Island site, which is to the east of Prudhoe Bay, not all the way to Kaktovik, but to the east. These sites, we're just studying the natural processes here. We picked these sites so that we could work in the fall and be well away from the subsistence hunting that occurs at the villages. And so we are basically working between villages in order to deconflict our presence there. Going forward, we'd like to work more with the villages on these projects, but this is a way that we can get started and basically be out of the way. At each of these sites, we have long-term moorings. We have moorings that we were established this summer, in summer 2019. Those moorings were recovered and turned around. Data was offloaded and they're put back in November of 2019. So I'll show you some of the early results from this work. At each of these mooring locations, we're measuring the waves and the water temperatures. And we think those are the 2 key things that are driving shoreline retreat. We're also measuring the circulation, the currents. So here's some results from one of those moorings that was again put out in the summer of 2019, was out until the fall and then was turned around. And it's just a histogram of the wave heights. And I would say that this is sort of what we expected to see. In August and September, the waves are generally small, 1 to 2 meters, and then occasionally there are bigger events up to 3.5 meters. 3.5 meters is still a pretty remarkably big wave relative to historic conditions, but in the new Arctic, I would sort of expect to see at least 1 or 2 events like that. The y-axis here is the number of observations, and there's an observation every half hour. So you could think of that as, there probably are, this is just, this 3.5 meter event here is really just one event, but several half-hour realizations of that event. So what was more remarkable in this data set, though, is what happened in October. In October, the sea ice extent was still very close to the annual minimum. And so the sea ice was very slow to return this fall. And there was still a very large fetch throughout basically all of October. And so the histogram for October, I think, is the most remarkable part of this data set. It looks like these yellow colors here. And so October had very frequent occurrences of very large waves. Some 3+ meters, even 4 meter wave events were relatively common throughout October. And I think this is really what the new Arctic is going to look like. And I will remind you that in October, this is a region that normally would have had some shore-fast ice already. And this mooring being close to the coast probably would have already been covered by shore-fast ice, and we wouldn't have measured anything, or very small waves at most. But throughout the whole month, we were measuring these much larger waves. So it's a whole nother month in which the coastline is exposed to wave action, exposed to warmer water temperatures, et cetera. And these are the things that are going to drive shoreline retreat. Okay, while we were out there in November, so we were out, that was the October measurements that I was showing you, and then we went out in November on the Sikuliaq, and we serviced the moorings, and we also did a lot of opportunistic measurements as we saw wave events occur. And so we saw, again, pancake ice. This is pancake ice now from November 2019, observed from Sikuliaq. We have some wonderful photos of it from John Guillet, who's a photographer who was embedded with us for the trip. And so I encourage you, I'll have a link at the end to some of their work and some of their outreach work, which was really a wonderful complement to this project. And so here's, again, one of our buoys in the pancake ice, and measuring the waves, also measuring temperature and salinity, and trying to understand the heat exchange between the ocean and the atmosphere, and the circulation patterns that, trying to understand what the whole system's doing in one of these events. So this is brand new data. Lucia's doing a lot of the analysis right now, but I can just show you a few teasers of the results and show you how this event unfolded. We were at Icy Cape during the event. Pancake ice was prevalent. In this synthetic aperture radar image, you can see that this is the coast. The ice is here all along the shoreline, and then this is all open water. The symbols are our moorings, and then we had swift buoys drifting freely throughout this, and we had a total of, I think, 8 buoys out at any given time that were freely drifting through here, so moving with the ice. They're in the ice reference frame as they go, and we would constantly be resetting them, picking them up, and going again. And the wave spectra from this shows something very similar to the earlier signals that I was showing, where there's a peak in wave energy as a function of frequency, and the black and blue lines are outside of the ice, and they have an expected f⁻⁴ tail, and the blue and the red lines are in further and further ice cover, and they're attenuated. They have less and less energy at higher and higher frequencies. And so we see something that's similar to previous measurements, but we have some slightly different ice types, and we have a model that's much closer to the coast and needs to be run at much higher resolution. So we're taking some of those earlier themes, and from a modeling perspective, we're pushing them into a much higher resolution environment and different ice types and trying to understand that attenuation. Also trying to understand what happened to this ice over the course of the event, because much of the ice actually melted towards the end of this 4-day event. And we think that's because of an influx of warm water through the Bering Strait, which was still occurring at this time of year. So look for more work on that coming out in the next couple years. The second part of this project is all about being able to model this and forecast this. So I'll just show a few things on how we're doing that. These are some examples for the modeling effort from 2014, because we had data in 2014, and so we're doing hindcasting of that. And again, this is Lucia's work, and Nirni Kumar and Eric Rogers helping with this. And the really distinct thing compared to the prior modeling work is we're using a different wave model. We're using the SWAN wave model, which is much better suited for coastal work and being at very high resolution near the shore because of its time-stepping scheme, relative to the global wave model that we had been working with to add ice before. So 2014 there's an example in the summer when there was a lot of ice near the coast, and you can see that in this plot here of ice concentration. This is the North Slope of Alaska. This is Point Barrow. Here's the main ice pack, and then here's this ice near the coast. And we are asking the question, how much did that ice affect the waves that reached the coast during the summer of 2014? And they affected it quite a bit. If you look at the wind field on the left panel, the winds are pretty homogeneous across the whole domain. And so if you didn't know there was ice, or you didn't have ice near the coast, you would just have waves that increase all the way to the coast and hit the coast. But when you know there's ice there and you include that in the modeling, then you get this wave field to the right where the wave heights are the color scale, and there's a really reduced area of wave heights here. And so that whole section of coast was protected by that ice for much of the season. So this is where two-way coupling, I think, is going to become really important in future forecasting and modeling of this domain. Is that to understand what's happening at the coast, you need to understand the interplay of the ice and the waves. And so you need an ice model that'll talk to a wave model, and a wave model that'll talk to the ice model, and vice versa. And there are a lot of people in the community working on that. We are getting closer to it, but there's still a lot of work left to do. So I want to leave you with that theme and this schematic of the coupled processes, and leave you with the message about our current project, that we're trying to take a lot of these signals towards the coast. We are at present mostly focused on how the ice affects the waves. So in that sense, it's a one-way coupling. We just need ice information. We give that to the wave model and figure out what the waves are doing. But where we're headed long-term is in coupling that back to the ice model, understanding how the flow size distribution changes, how the ice evolution changes, etc. So I'm going to wrap up there with some thank yous. A lot of this work is funded by the National Science Foundation, the more recent coastal project, and then the work out in open water is mostly funded by Office of Naval Research. We've had great support from the National Ice Center, providing a lot of remote sensing products throughout all these field campaigns. NSIDC has been really helpful with their data archives. The research vessel Sekuliak, which I'm showing you a picture of here, has been a wonderful platform to work from, and it's just a great resource for working in the New Arctic. And then I've tried to highlight the different collaborations and students and postdocs working throughout the slide deck, but I'm sure I missed a few, and it's really wonderful to have so many great people to work with. And then I'll leave you with all of these links here to the different projects. This last link here, the CODA project, that's the coastal one I finished talking on. And if you go to that link, you can also find the Ice in Motion outreach effort that has really wonderful video and photography from that last trip we just did in Sequoia. So really nice if anyone's looking for some outreach material or something to use in a classroom setting. There's a lot of great stuff there. So I think I'll end there and I'll hand it back over to Betsy to do some moderating of questions.
Thank you, Jim. That was a great presentation. So we will begin our question and answer session now. And just as a reminder, please type your questions into the chat pane and I will read them. We've got a few questions lined up already. First one is from Brendan Kelly, who asks, can you say more about the stable wind speeds in your data set and your indication that others have seen increasing speeds?
Hi, Brendan. I think the stable wind speeds in that data set are because we averaged over that whole domain, and that's a big domain. It's really most of the Beaufort and the Chukches. So, you know, the synoptic weather patterns are big enough that I think that any trends get blurred out in that big spatial average. I think there's some nice work by Jim Overland looking at how the Beaufort Low is shifting, and there's some other work by Wang et al. 2018 looking at probably some increase in the wind speeds. If you look more specifically at a few places along the coast, the way the lowest track is changing a little bit. I think so. I highlighted that nuance because I don't want to try to refute the other results that the winds are not changing. I think they probably are changing, but I like that result as showing that we don't need to invoke changing wind speeds to see the dominant changes in the waves. The dominant changes in the waves, I would argue, are because there's more space and time to make those waves. We don't need more wind to explain it. It's really about having less ice. That's the dominant thing that's driving it.
Thanks, Jim. Next question, I think, is from PC Taylor. What are the changes in wave climatology serving as a positive feedback on the lengthening of the sea ice melt season and delay in fall sea ice freeze up?
That is a great question. That is the sort of first order hypothesis that we had when we started on all this. Is that feedback mechanism strong enough that you can imagine it running away, much like the ice albedo feedback can run away, that if you have bigger waves and they break up more ice, now you have more fetch, now you have more waves, and you just keep going, right? I would say we have not seen evidence of that in the way that I would say is statistically reliable enough to publish it. We have not published on that feedback, even though it's something we've been chasing. And I think there are two reasons for that. One is that I think in the springtime, in the original breakup, that's still thermodynamically driven. That's still really about the melt ponds and about, you know, the increase in solar radiation and then the warmer air temperatures and that whole ice albedo feedback. That spring loss of ice is really still mostly thermodynamic, and it's not mechanical. It's not associated with the waves. In the fall, the wave story, in terms of maybe how it delays the ice advance, that's also tricky because I think what we've mostly seen is that fall, that some of the waves are actually enhancing ice growth. If given the same heat fluxes, the same air-water temperature difference, let's say 100 watts per square meter being lost from the ocean in an ice-making process, given those conditions, if you have waves, you'll make pancake ice and you'll make faster ice than you would if you had no waves and were making nihilus for the same heat flux. So it's actually an ice enhancing process in some ways. So that's also complicated. I think the other part of the story is that many of the things that would happen in a wave-driven scenario are very event-based. And we do not do a good job, in my opinion, of sampling events or of modeling events. We do a good job at the averages, right? We know what's happening on average throughout the domain. The time steps in a lot of these big models are half a day or a day, you know? And so the real nuance of what happens in an event, we sort of miss. So I think things like the Great Arctic Cyclone in 2012, the waves were part of the story in that rapid ice loss, but you can also explain it with just the winds and the water temperatures. So anyway, I think that feedback mechanism is still a valid hypothesis between the waves and the ice and the breakup, but we have yet to have a data set that really conclusively shows that it's a dominant mechanism. But I think it's definitely something to worry about, and yeah, we don't have it proven yet.
Thanks. Next question is from Stephanie Reinders, and she asks, what wave energy sinks are included in the SWAN compared to wave watch?
So what we're putting into SWAN is actually the same algorithm that's in WaveWatch 3. So if you're familiar with that, some technical details here, that's IC4. And there's a review paper that we wrote about the WaveWatch 3 modeling, and we have a table where we outline the different wave dissipation schemes in WaveWatch 3. And we took what I would say is the most popular one of that, and that's what we implemented in SWAN. So in that sense, it's the same. It's a set of polynomials that that attenuate each frequency, and those are tunable, and you can input them based on ice type. And so there's one for real flows, and there's one for slushy, mushy pancakes, and we're still calibrating that. But and it's purely an attenuation thing, right? We're not treating scattering; we're just treating attenuation, which, in my opinion, is the dominant thing that we see. I think in our data we don't see a lot of evidence for scattering of the wave energy, even though it's a hot topic mathematically. We see a lot of evidence for just dissipation, just energy being lost. And I think most of that's going to the collisions of that piece of ice and into the turbulence in the water below. But it's truly an energy loss, not an energy redistribution.
Thanks. And just to stay on that topic, I think Jim Hunt has I'm not sure if it extends the question any further, but he asks, does the SWAN model work better than the WaveWatch 3, even on ice-free Beaufort Sea in the 21st century, August and September?
I think the SWAN model should in the end work better closer to the coast because of the implicit time stepping. So can resolve the coastal bathymetry better. We'll do the shoaling and refraction better. I would say that, in my mind, a full system needs both, right? The Beaufort and Chukchi, the whole Western Arctic is large enough that we're better off to run the WaveWatch 3 on that whole domain for efficiency and for it's already linked up with NavGem and those things, and then you drive SWAN at the boundaries of a coastal SWAN with that WaveWatch 3 output. But then I would expect SWAN to perform better in shallow water. I mean, there's 30 years of work with making that go, so we're relying on a lot of that. And then the elephant in the room is how well do we tune the ice schemes for that, and truly the elephant in the room is how well is SWAN going to do with shore fast ice, which of course is much mechanically stronger and probably able to dissipate wave energy much more effectively. And that we haven't tackled yet. I think it is something we really need to do, but we are not there yet. Oh, Betsy, you're muted.
Thanks. So a question from Andrew Roberts. Can Jim describe in more detail how his modeling is included landfast ice evolution?
I think I just answered that with we have not yet, and we obviously have to. The shorefast ice can extend many kilometers out from the Alaskan coast, and it's grounded, it's locked into the shore, it's going to be a lot less inclined to move than the rest of the ice, and so we don't have a great data set of that yet. That's what those moorings are for. The spring breakout, I'm hoping that some of those moorings survive. I'm not naive enough to think that they all will, but we put out a lot for that reason. And we'll be able to use SAR images that we're getting from National Ice Center to see exactly when breakout is happening. And then, we'll get that wave data back and we'll see, just how things responded within the shore fast ice as the spring breakout occurred.
Thanks. Okay, I'm keep tracking questions. Another question from CU is it essential to take ice types into account in wave interaction and modeling?
Yes, I think it definitely is. The 2016 paper by Eric Rogers showed that if he knew a posteriori, after the fact, what the ice types were, he could make that wave model just dance. He could make it really agree with the observations within 5%. And it really did sort by ice type. It wasn't just arbitrary tuning. It was, if you have these bigger rafted pancakes, you use these coefficients. And if you have these small mushy pancakes that are kind of, baby pancakes, then you use a different coefficient. And if you have just frazzle, you use this other coefficient. And if you know that, then you can make the model do really well. But we often don't have that a priori, right? We don't have that from the ice forecast. The best thing we have operationally is just the fraction, the ice cover. That's it. Maybe thickness. But having details of the ice type, and especially at that resolution, that's something have yet. So we do have a problem in this. If we're just talking about the forward wave modeling, we have a problem of garbage in, garbage out, right? If you put in very poor ice information, you're going to get very poor results out of that wave ice model. And I think that's a huge issue going forward. What we've been able to do that's been really successful on the modeling has been when we have gear in the water and those buoys all take pictures, they take images of the ice type. They have a proxy measure for the ice thickness with a little up-looking sonar that's mounted on board. And when we get that level of detail for the ice type, we can make a lot of sense of the data, but we don't have that for forward modeling or forecasting most of the time. It's a big issue.
Okay, thanks. Next question is from Chase Stout with BOEM. He asks, can you speculate on what increased wave energy into the water column will do to the heat flux into winter bottom water formation?
That is a great question. Again, Maddie Smith, a PhD student who just finished recently, she has a 2019 or 18 paper where she looks at exactly that question. She says that now we've got big mature wave field. Will that provide additional mixing to the upper ocean, which would deepen the mix layer and allow basically you to reach a little further into the ocean to get the heat that's stored there? So quick background, the Arctic Ocean's all salt stratified, and so there can be a lot of heat stored just below the surface, maybe 20 meters down. There's a near surface temperature maximum, and a bunch of the heat that comes in from the bearing will subduct and get sort of stored down there, and it's sort of laying in wait to be released. And we know from other work across the global oceans that waves and in particular Langmuir turbulence enhance mixing in the global oceans. And so now we have an increased wave climate in the Arctic that's a new phenomenon, and we can expect to deepen mix layers and pull more heat out of the ocean, basically. Our global results on that are that the waves add maybe 20% to the wind-driven mixing. So I will just rely on that number, lacking something much more robust than that, maybe we would have mixed layers and things that are 20% deeper throughout the Arctic. And that can be an appreciable amount of heat. Maddie's paper showed that that definitely was, for this one event she looked at, was quite a bit more heat coming out of the ocean and coming out at a faster rate, right? We do everything in watts per square meter. And, it was something like a couple hundred watts per square meter instead of 100, something like that.
Thanks. I think we'll have to close pretty quickly. I'll ask one more question from Bjorn Ellenson. Have you seen wave-induced ridging and/or rafting in the marginal ice zone? Do you anticipate or expect that the flexural breakage in the dominating mechanical impact of the wave? What do you expect?
I definitely expect it to occur. We've seen a lot of rafting in the fall when the ice is, still pretty new and pretty weak, and it's either the rafting of pancakes as they form, or if you've made a bunch of sheets and made finger rafts and things like that, and then a wave event happens, they'll all kind of get pushed on top of each other, and quite a bit of rafting. Haven't seen as much ridging that is very clearly wave driven. It's that sometimes in those events it's hard to tell what the large scale wind is doing and what the ocean circulation patterns are doing. But certainly rafting, especially in the fall, I think is very common and is pretty wave driven. I think in general, the Western Arctic has really weak and thin ice in general. A meter thick first year ice is kind of a typical thing now. So I think it should be pretty easy to break that, for waves to come in and fracture that. So I'm expecting that to be a pretty common thing to happen.
Thank you. I think we'll have, it's an hour, top of the hour, so I think we'll have to close up. I have recorded a couple other questions that I'll forward on to Jim. Maybe he can answer those offline. Want to thank you all for participating and mention a couple different opportunities that are coming up today. The IARPC is hosting a NASA Arctic Programs Chat Officer that starts right at 9 o'clock here, or right at the top of the hour, 9 o'clock Alaska time. And also the deadline for abstract submissions to the Polar Technology Conference is today at 5 o'clock Alaska time. I encourage you to submit any abstract submissions. And on behalf of ARCIS, I want to thank you all for participating today. A special thanks to Dr. Jim Thomson for this excellent presentation. Really appreciate all the interaction we've had from the community. Today's webinar will be archived and available online within the next few days. It'll be at arcis.org Research Seminar Archives, and that will be sent to everybody. And you can visit the ARCIS homepage for more information. We welcome your feedback to today. We're always trying to improve our webinars. So if you would please take a link or follow this link. It's also in the chat to a quick survey on SurveyMonkey. We'd appreciate that. As it's a minute off and we've got a busy day for everyone today, I want to close the seminar. And again, Jim Thomson, thank you very much. It was just an excellent seminar. Have a great day, everyone.
Thank you very much. Thank you. Very good.